Thank you. I hope I live up to it now. So I'm going to talk about ectd-based Postgres HA cluster. A lot of the talk so far today have been more about the CoreOS as a platform, as a OS. Today, mostly I'm just going to talk about how we use ectd at Compose. A little bit about me. I'm Chris Winslett. I work at compose.io. On Twitter, I am at Winslett. What is Compose? Compose is a database hosting service. So you can come to us, you can spin up a database immediately, you get production grade out of the box, you get backups immediately, you get replication, you get failover. We run MongoDB, Redis, Rethink, Elasticsearch for customers. A lot of this talk is going to be how we began analyzing tools for using, experimenting with Postgres. How can we bring Postgres to our customers with those same set of requirements? One of the core features of our platform is that as you grow your data in your database, we actually give you more resources. So you get more RAM, you get more CPU, you get more I/O. So it just scales continuously as you use your database more as you grow. So what is Compose? This is going to kind of set some of the requirements that we built for on top of this project. A lot of our customers are self-service. Those customers come in, they just want to create a database. You guys are developers. You don't really like talking to people mostly. You just want to use the technology, and you want that technology to work immediately. I'm kind of the same way. I signed up for a service recently. When I signed up, someone called me on the phone. I didn't want to talk to someone on the phone. I just wanted to try the service and use it. So we expect our platform to do the same thing. As part of that, when things go down or when there's issues on the back end, the customer doesn't want to experience those issues that they're actually paying to be relieved of. So it's self-service. People just want to use the service. We have two sets of customers on this project. One was our customer who pays us money, who uses our service. The other customer is our ops team. Our ops team does not want to wake up in the middle of the night. And just like the guys were talking about earlier, you want to have so many servers that each individual server does not really matter. That's part of why we have replication, part of why we want to do high availability. That each individual Postgres is important. However, one data node is not important. So as long as we bring that back online, it will join the group, join the cluster, and participate with the cluster and be healthy. We want our product to be awesome for our customers and our ops team. So those are the two types of people that we're trying to solve for. And then the question became, can we run Postgres on this? The other databases that I showed you a second ago, Elasticsearch has a sharding mechanism where it replicates through sharding. MongoDB has replication built in out of the box, so you can just use replica sets. Redis has Sentinel now, so it can do high availability and failover. Rethink also has replication, although no failover yet, but they should be getting it soon because they're looking at Raft. So could we run Postgres, which is a traditional SQL database, with these same types of requirements? So requirements are replicated, highly available, no human interaction for failover, both for our customers who use the service and for our ops team. And we also want to minimize core engine modifications. We didn't want to launch a Postgres that has more edge cases. We wanted to use core Postgres as much as possible. Also, so the requirements from our customers' experience also was we want customers to be able to interact with Postgres at the deployment level. We don't want to just give them a database endpoint. We want them to actually be able to use Postgres, say create database, create roles, use everything, so have the full Postgres experience. We also do not want them to have to change any of their code for failover mechanisms, so they would need a place to go. So when we started this, we laid out all these priorities, we laid out all these requirements. Some of these we hadn't fully fleshed out when we first started this project. So we investigated rep MGR with pgpool. It required human interaction for a failover, does not do Postgres streaming. pgpool is flaky on failover. Postgres replication, streaming replication is awesome, but it does not do failover automatically. Bidirectional replication is kind of the way it seems like things are going with Postgres. but it requires a patch on the core engine. We didn't know if we could really truly get support if something went haywire on that, so we wanted to stick with the core stable Postgres. It only runs one database per cluster, so you actually have to pick the database. So those things weren't meshing with our requirements. Is automated failover too ambitious for Postgres was our next question. But it wasn't, because we'd kind of learned some things through this, through the investigation of the tools I mentioned a moment ago. We'd learned some things, and that is that people are doing it. They just, there's not necessarily automated ways to go about it yet. Or there's not necessarily a default template for going about it yet. So the things that we learned is that Postgres should not be the canonical data store for its own state. And that was because if you have a leader, you have a primary, the way that Postgres streaming works is that information gets streamed over to the secondary. So the secondary, the follower, only has information about that it's been streamed to. So if there was a network partition between the two and it didn't get streaming data, it couldn't give you canonical information about the health of the entire cluster as a whole. So we looked at surf. Surf is not consensus-based. Then we actually looked at console first from HashiCorp. We did that before we looked at ectd because there was actually a lot of nice tools. I'm going to kind of take you through the landscape and how we looked at console first and then ectd. So console, we built, console looked like it was going to be the thing that we needed. It had locking, it had sessions, and it had health checks. The locking was a way for us to lock a particular key. The sessions enabled us to lock that key and say which session owner owned it. So if you think of like a 2-data node Postgres, one would own the session, and or one would have a session, both would have sessions, and then one would own the lock. And then based on whoever had the lock, you could say that person's going to be leader. Well, that worked out, and then we did health checks too, which were actually really amazing in console, because then you could run health checks within each data node. So you would actually run console alongside Postgres, and as that console was running alongside Postgres, it would actually check on the health of Postgres right there. So then you could see that this particular Postgres is healthy. We did a prototype. The code's at mongohq/console HA. In this first iteration, you'll see tight coupling between the console interaction and the HA decision loop. Now, one thing that really guided us a lot on this, on our later ectd implementation, is the leader election here for the for console's guides. In this, it will talk about how you can do leader election within console, and it talks about how to do it with the locks and with the sessions. That gave us enough information there to kind of come up with a console diagram for our decision tree for HA. Don't necessarily look at each individual node on this decision tree, but just kind of notice how complex it is. We actually went through a lot of iterations trying to figure out the exact decision tree that we wanted. So this is kind of one of the early decision trees, and with this one, we actually had 3 runners. We had console running in there. We had governor, which you'll see again in a minute. And then we also had a state handler, which was handling Postgres. Now then, eventually, console got to be this diagram, which looks a lot more complex. So we went from slightly complex to a lot more complex. So the console results, the results of our prototype, where we just wanted to see if we could do HA failover. It was awesome. Console allowed us to shrink and grow our Postgres clusters. Whenever we would deploy a new Postgres to a cluster, so let's say we had 2 data nodes, we wanted to deploy another one, we could deploy a console with it. Console would actually join in on that cluster, and it was growing and shrinking. We could remove one of them, and it worked really well. And then health checks to prevent unhealthy secondaries from requiring the lock. That was until we ran into the core issue that we had with console. That core issue is that console takes out a 40 gigabyte virtual memory allocation upon start. And so if we wanted to run one of these with every single Postgres that we have, that means that we're running a couple hundred Postgreses on one server. And that would mean that we would be running a couple hundred consoles on one server. That would mean that we would have a lot of wasted resources. So we had to find something else. What we learned from console is that HA Postgres is possible. We learned the algorithm that we were going to use later on, but we needed to use resources more wisely. So because of what we had learned, the switch to ectd was quick. So console, like ectd, both uses a HTTP API, and because of that, we could just change out a couple of HTTP calls. So it was very quick. We just kind of switched over the prototype. You'll see that we've iterated through our diagram. We actually only have one runner now. The diagram's very simple. I'll actually show a lot more of this in higher detail in a minute. But we have a startup process at the top, and then we have a running loop at the bottom. The startup process either initializes Postgres if the data directory is empty. It also uses some of etcd's core features as far as like some of the API features. And so the initialization startup process at the top and then running loop at the bottom, that running loop manages a state, whether it's a secondary or a primary. So etcd's features used. We use the consensus, of course, because Postgres does not come with consensus. So that's just being used out of the box. We use recursive, TTL, pre-value, previous exist. With those particular values, we can then create a state machine for Postgres. So what recursive does is it allows us to, whenever we start up our script, we'll actually do a post members saying this is a new member joining this cluster. But then what we can do later with Postgres is we can actually say, tell me all the members who have joined this cluster. And so then we have a list of all the people who have joined, all the other runners who have joined this cluster. And so then we know information about our cluster. So Postgres doesn't have that information, but we're storing it in etcd. And then as Postgres is running, we'll pull it out of etcd with recursive true. Now, keep alive from a Postgres leader. The lock mechanism that we use within this project is a TTL. So we use TTL equal 30. Oh, that's a typo. That should be TTL, not TLL. So TTL equal 30. Every time that loop runs, it'll update the TTL key. Pre-value used in conjunction with the TTL. So leader, TTL, equal 30, and previous value equal member. So what this does is whenever the leader is going through its loop, it makes sure that it is still the leader. That pre-value says, I am still the leader, and if I'm still the leader, I want to set the TTL to 30 more from what it currently is. We use previous exist for two things. Used to create a deployment and initialization race. Imagine this, a new deployment comes up, no data exists yet for Postgres. We have two members, and those two members say, I have no data, what do I need to do? And so what they know they need to do, the governor process, actually races to initialize, or to set a value for /initialize, preexist. Preexist equal, that should be false. Yeah, so preexist equal false. And then it sets that key, and so that can not initialize. Now, we improved this with iteration through, we decoupled some of the classes. So we decoupled our HA decision process, our etcd state interaction, and then our Postgres handler. Now, we're going to get to code in a minute for a live demonstration. And also, you'll have code that you can actually monkey with and see how this stuff works. So, issues with etcd. The one issue that we had with etcd was actually resolved recently. It was using a lot of CPU, using a lot of just system resources on the RAF protocol. 205 actually solved much of that. So I gave this presentation at a CoreOS meetup a while back, and that had not yet been resolved, but now it is. And actually, etcd is a very, very nice, has a very nice place in our system now, where it doesn't use a lot of system resources, and it works well. Also, etcd, unlike console allowed us to grow and expand these consensus state management systems. So console allowed us to grow and contract. ectd does not. ectd is best run by deploying it as a cluster, as a static cluster. So what we actually do now is we have a ectd cluster running, and then our Postgres clusters talk to it. So it's console was running beside ectd, and we actually moved that out. Okay, time for a live demo. We'll see how this goes. Okay. Okay, can you see that, hopefully? Let me make some of the screen a little bit bigger. Okay. Oh, let me give you guys some code, some URLs, so you can actually go out there and actually start seeing how this code looks before we start any of this. Okay, this is the project. So if you go to github.com/compose/governor, it's runners to orchestrate high availability for Postgres. We tried to put all the information right here that can help you get started. So you just basically start up ectd, start up a governor PY with some Postgres information. All right. Okay, so we're going to try to start up Postgres. Let me show you some of our decision tree that I was talking about earlier. Okay, now what happens in the startup process with the concept is we have a governor runner that is a Python script in this repo. We have a governor runner, we have etcd, that is going to be our state store, and then we have Postgres. Postgres is the dummy in this relationship, okay? Postgres does whatever the governor tells it to do, whatever the governor running process tells it to do. etcd gives us some nice mechanisms that governor then uses to manage this state. So this startup process is for our governor.py script. The first thing it does when it comes up is it makes sure that it can connect to etcd. Without etcd, the governor is useless because it knows nothing about the state of the cluster. So the first thing it does is make sure that it can connect to etcd. The second thing governor does is check that the data directory is empty. If it is empty, it tries to win that race to set an initialization key. If it wins that race, it takes over as leader. It initializes the database, takes over as leader. If it loses that race, then it waits for a leader to be initialized in the cluster because it is not the leader. So let's see how this works in process. So PG-based backup from leader. Let's see. So now let's run this. So what I'm going to do first is I'm going to start the governor process without etcd running, so that we kind of see it wait for etcd. Okay, as you can see, it's just chilling until it can talk to etcd. Isn't that right, Kelsey? I changed my error message there just for Kelsey's dog. Okay, so now we've got our etcd, we've got our governor that's just running and talking to etcd, or trying to talk to etcd. But etcd is not alive, so you can imagine what's happening here. We have a distributed system. We run within containers. We tell our deployment to just go right now. We say go. And what happens is you have a lot of race conditions going on there. You have some that are booting up, some that are booting up over here, some that are booting up on this other server. So right now, one cluster, one capsule or one container that beat the others, now it's waiting on etcd to come up. So etcd. Okay, etcd comes up. Now, it talked to etcd right here. It knew that its database, it knew that its data directory was empty. So it initializes the data store, or it initializes the database, which is basically just initdb get started. Okay, so now let's see what happens. Oh. Okay, so now let's add another runner to the mix. So if you remember, what I said was each member is actually updating ectd with its state information as it runs. Come on. There we go. So ectd has the state information. Each governor process is saying, hey, I'm in this cluster. So what we can do is we can go to governor, and we can actually start another governor process, Postgres 1. All these Postgres files here are just configuration information about Postgres. Basically, it tells it what port to listen on, give it a username password for replication, give it a network for replication, and then pass them some parameters on start. It says hot standby, which allows us to query secondaries, archive mode on, which is required for streaming replication, some of that stuff. So what this does is it just gives us some information, or it allows us to configure Postgres. So let's do governor, Postgres 1. So that is our new Postgres that is running. So what's happening on this is that it actually started so quickly because ectd was already running and it could connect to it. It tried to connect to it, tried to set the initialization lock. That initialization lock was already taken by our previous Postgres. So this other one comes along and says initialization's already happened for this cluster. And then what happens is it looks for a leader based on a known key. So we have a particular known key. It finds that leader, and then what happens is, because we have a username and password for the cluster, it starts initializing as a secondary, and now it's a failover. So over here on our left, bottom left, we have no action, I am the leader with a lock. On the bottom right, it says no action, I am the secondary, I am following a leader. So what we had is we started Postgres, we started our cluster with one Postgres. We added a new one that immediately joined the cluster, became healthy. Now we can add more, or we can actually begin kind of talking with Postgres. So let's see. So we actually run HA proxy in front of this Postgres. You'll see some of the tools there in the repo. If you go to it, so we're running that, so we should be able to connect to it. And if we do list here, you'll see that the database is running. Now, if we stop one of these, let's stop our primary. So we shut down the primary. Secondary says, hey, I can't stream logging information anymore. From our configuration information from our process, what happens is that loop is running. And within 60 seconds, ectd will release its TTL lock, its leader lock. Once that key gets released, what happens is it'll use the check and set to make sure the secondary will use a check and set to become primary. And you'll see right here, it's promoted itself. So what the governor does is it uses ectd state to make sure that we don't have multiple leaders at the same time, and it begins taking over. So now what happens if we actually start this other Postgres back? This other Postgres comes back. One of the things that we learned that MongoDB did well was that whenever a cluster comes up, it starts in secondary first. Postgres starts as a secondary. It checks itself, makes sure everything's okay. Make sure that it can start, and then it actually starts following this other leader. So what happened is we had Postgres 0 as the leader. Postgres 1 joined the cluster. Postgres 0 went down. Postgres 1 promoted itself, and now we're actually rejoining the cluster with this secondary. So now we can actually do many different Postgreses. So P governor, I'm trying to wrap this up real quick. We can actually throw a new Postgres in on this cluster. So governor, So if we throw another Postgres in on this cluster, which I've got another Postgres YAML file, so I have Postgres 0, 1, 2, 3, or 1 and 2. So we throw another one in there. What happens is governor connects to ectd. So governor connects to ectd. Postgres is managing the state. What happens is this, this governor posts a member to the other, to etcd. The runner picks up that new member and says, hey, I'm going to add it as a replication slot within Postgres. Everything just happens and just works. We actually are running this in production at Compose. It's a little different code base. We've got a couple more tools based on our own use case. What we're calling this is a template for you guys to kind of start thinking about how you can make databases that are traditionally not high availability, make those into high availability databases. The way this is built, you can actually go look at the code. The way this is built, we have a Postgres runner, a Postgres handler. You can take that Postgres handler out, replace it with a MySQL handler, replace it with some other database that does not have high A, and go from there. Are there any questions? All right. Well, thanks so much.